Good afternoon. My name is Leo.
I'm Matthew.
And I'm Tim.
So we're going to be discussing solar cells or photovoltaic cells, which essentially work by converting light in the form of photons directly into electrons, which then provide electricity through both chemical and physical reactions. So solar cells are an important step in working towards a more sustainable and renewable future. Their importance derives mainly from the fact that the sun itself is one of, if not the most potent energy sources within our reach. In fact, a single expanse of solar cells in a sunny state, such as Nevada, is capable of powering the entire nation with solar energy. So, to maximize the power capacity of our solar cells, nanoscience plays a major role. So it does so by greatly increasing the surface area in dye-sensitized cells, the solar cells we worked with, therefore improving the cell's ability to absorb and manipulate light. So given the potentially devastating effects of our current carbon emission levels on the climate, the importance of research in this subject of solar cells is more important than ever, despite the fact that it's very costly. So in this cartoon, which depicts a representation of the solar cell cycle through a baking process, we see these three illustrations in the corners, which we'll kind of get to later, and then this main cycle, which represents the solar cell cycle. So we have two ovens, one set to 375 degrees and one set to 50 degrees. And we can see that the pies being baked in these ovens are very different. The one on your left, they fully rise and they satisfy their consumers, which then results in money, or electrons, which then provides room for more materials, and that kind of keeps the process being continuous. It keeps it going. In this one that is set to 50 degrees, the pies aren't baked very well, and we can see the people are very sad and don't give any money, so they're not really helping in the process.
All right, so I'll be getting more into the science of this cycle of the photovoltaic cell. So this is a different type of solar cell called a dye-sensitized solar cell, which is different than the common silicon solar cell. So basically, this type of cell starts out with energy from the sun coming down onto a dye. In our case, we use a dye called anthocyanin, which comes from raspberry juice, and it's a red dye. And so basically, this reflects all the red and absorbs all colors, mostly being green, and uses this energy from the light to charge different electrons to bring them up to the next energy level. These electrons, in turn, are able to do two different things. One, go down an energy level, which is the easier thing to do, but it's also the thing you don't want it to do to provide energy. Or it can go on to the next step, which is to transfer onto the titanium nanoparticles. So the titanium dioxide used in the next step is so that the electrons that went up in energy level in the dye do not go back down. So also, why are these titanium nanoparticles instead of just a flat sheet of titanium? So this is so that since we know that nanoparticles have a much higher surface area, exponentially higher, so this makes it much easier to put more dye on it and thus absorb more light to power up more electrons to get a higher efficiency rate for the cell. After going on to the titanium nanoparticles, it goes on to another conductor. In our case, we use something called fluorine-doped tin oxide. And this basically is a conductor, but it has a special property where it's clear. So this has to be a clear conductor because it has to allow light to go through in order for the photons of the light to hit the dye, which then starts the process. After the FTO, or the fluorine-doped tin oxide, it moves along a wire, and this is where you have your power output, which can be a multimeter or a fan or anything else you want to attach to the solar power, and then to another FTO plate. From this plate, it goes on to an electrolyte, which we use iodine, and this basically restores the electrons back into the first dye and finishes that process.
All right, so I'll explain the analogy. We'll start with the middle cycle because that's the most important part, and then we can go to the corners. Now, starting from the beginning, our ovens. We have some ovens here delivering some lovely thermal radiation to our pies. You can see, Leo touched on this earlier, but the one on the left is at a much higher temperature than the one on the right. And so the pies are actually rising here, and they're not doing nothing here. So this is analogous to the fact that sunlight from the sun comes in a spectrum. There's a whole bunch of colors. There's a lot of reds, yellows, there's a smaller amount of blues and purples. And so what that means is the dyes that we use, they take a certain wavelength for the electrons to get excited. We use some red dye, the anthocyanin, and so those will obviously, they reflect the red light out. That's why we see them as red. And they absorb the green the best. And so in that case, they take that specific wavelength for those electrons to be excited. But if the wavelength is wrong, or in this case, the analogy is the temperature, then the pies don't rise and the electrons don't get excited, and then they don't get transferred to happy customers. So going back to our correctly risen pies, they go down towards the happy customers. And in this case, the customers are like the titanium nanoparticles. They accept the pies, and then they keep it, and then they transfer it over as money. And this is analogous to sending the electrons into a current, which then they can get harvested into a generator to charge your battery or your Tesla car. And so after that, the electrons go back into the electrolyte, which is basically ingredients, right? This electrolyte provides the supplies for the next cycle to occur. And so this process goes on, and then electricity is generated. Now, up in this top left area, we have the person at the top that has 4 smaller pies, and he's pretty happy. And there's this person on the bottom here, he's unhappy, and he has just this one massive pie. And I think what that's trying to convey is the concept of nanoparticles and surface area. Now, the smaller pies, as you can see, they have a much larger surface area for a given volume. The amount of pie can be the same between the 4 pies, the 4 smaller pies, and the 1 big pie, but they have different surface areas. And so what that means is the smaller pies, they bake quicker and easier. And then so what that means is then the electrons can get excited more easily. And that's one of the reasons why we use nanoparticles. That's why we use titanium dioxide nanoparticles. Down on this bottom right, I think this is an example of voltage. And so what that means is you can see this top guy has a really big pie, and this bottom guy has this really flat pie. And so in like the same batch, this person is making a whole lot more pie than this person. And then, so basically what voltage is that each electron has a specific amount of energy. Higher voltage means that that electron has more energy. And so what that means right here is if you're producing the same amount of pies, but you have a higher voltage, then you can generate a lot more current. Or in this case, deliver a lot more pies to a specific amount of people.
Thank you. Any questions? Okay, so his question was how to make these solar cells more efficient, I guess, and how to make them commercially available. So the main problem with dye-resistant sensitized solar cells rather than silicon solar cells is the efficiency. It's around 15% less efficient. And so the main reason for this is for actually 2 reasons. One, silicon has a much better, it's called a band gap. And so basically the silicon band gap is 1.1 electron volts, and the ideal band gap to absorb the most energy from the light is 1.2 to 1.4 electron volts. So silicon's really close to this and probably the material that's closest to this ideal band gap. However, the dye is not. And so another problem with this is how I mentioned before when you first start the process, and right when the dye absorbs the first amount of energy from the light, and it goes up an energy level, there's 2 things that this electron can do. It can either go down in energy level, which is what the electron naturally wants to do, or it can continue the cycle and go to the titanium dioxide nanoparticles. And so basically most of the electrons do go down that energy level and don't go onto the nanoparticles, and only some of them, which is the 15% efficiency, so only 15% of those electrons actually go onto the nanoparticles, and this leads to a major loss in efficiency.
I'll go a little more into like the comparison between this dye-sensitized solar cell technology and the silicon solar cell technology, which we see all over the place. Now, the silicon technology, it's more expensive to actually process the silicon, but as Matthew mentioned before, it's a lot more efficient due to that band gap being 1.1 electron volts, so it's very close to 1.2. Silicon cells are really rigid, and so they're not flexible at all. But these dye-sensitized solar cells can be flexible, and so that might be one advantage as to why you might use the dye solar cells as to the silicon solar cells. One downside of the dye-sensitized solar cells is that, well, first of all, they're less efficient. We talked about that before. And they also, they're prone to degrading with exposure to the atmosphere. So that's more of an engineering problem, but obviously it's going to increase R&D development prices up if you're talking about actually rolling this sort of technology out on a wide scale.
I think so. The titanium nanoparticles that we use are around 250 nanometers per particle, and that's to maximize surface area. And so I think it's more just of a material, it's harder to go smaller problem. And so more than just us not doing it. Because the smaller you can go, the better. Because the smaller you go, the more surface area you have, and thus the more dye you can get onto it. And so basically I think that we would like to go smaller, except it's more of a material limitation rather than us not doing it.
Okay, so that sounds so good. So first, they are 250 nanometers. They are 250 another unit. No, littler. Angstroms. They're 25 nanometers. And I could make you 5 nanometer titanium right now, but it would be worse. And so now your question is, why would it be worse? And I will help you with this by saying that 15% efficiency is not that only 15% of the electrons get onto titanium. Actually, probably about 80 or 90% get onto the titanium. But then what do they have to do after they get onto the titanium? What is their fate?
Okay, so obviously they have to enter, they have to hit the film, the transparent conductor for it to enter.
Right between there, what do they have to do?
They fluoresce if you don't trap them.
No, between after they get on the titania and they get to the transparent conductor, what do they have to do?
Get there.
How do they get there? Yes, they have to get there.
Transmit.
How do they do it?
They jump from nanoparticle to nanoparticle.
Exactly right. Why might it be bad if the nanoparticles were smaller?
It'd be too difficult for them to reach the next one.
Yep.
They'd be insulated.
Goes up. And then that's one place you lose a lot of your electrons. The resistance in that process. And then also some of them, after they go onto the titania, still go back to the dimolecule. So that's the other place that you lose. So that was really good. Okay, so two comments and one question. How you got voltage out of a little man with too much coffee is really, I'm impressed. I want to hear what the author says the bottom right corner is supposed to be. Also, I'm afraid I really disagree that they're pies. I think they're muffins.
Okay, so the sunlight would be the heat from the oven cooking the pies. And so basically there are two different ovens in there, and one of the ovens has a different wavelength than the other one, which you can see through how close together they are. And so one of them's good, one of them's not. And so basically this change in wavelength would be the red versus the other colors of each of the wavelengths.
So now the question is, what aspect of what the sunlight does is not captured? So remember we said no cartoon captures everything. And part of your job is to say what is captured and what isn't. This is not a critique of the drawing. This is just intrinsic. Okay, so how does the oven, what aspects of sunlight does the oven not capture? What is the sunlight doing? It's doing what? So that is a mic.
Exciting the electrons in the die.
So how is excitation captured here?
Would it be the happiness of the people? So they're getting happier. So you can see the comparison from when it's not the wavelength's not correct, or ideal, to when it is.
I mean, I don't know. I mean, it's a cartoon. It's pies and flour. But a concept that is not so clear is the idea that the electron goes from a low energy to a high energy, where the last one that didn't capture some of the concepts that this did showed that sort of lifting gumballs up. So every one of them will include some concepts and leave some out. But it's just interesting to point out where there's concepts that are.
Well, the change from the basic materials to the actual formation of the pie kind of represents the excitation of the electrons from their relaxed state to a more excited state. But
I could buy that, although a cooked muffin seems sort of relaxed to me. But I'm not.
got it.
Okay. All right. Thank you, guys.
Thank you.